Hi, this is Dr. Liu. Let's go through the introduction to Python. This is one of the labs. So let's get started. And the reason that we want to do this is we want to incorporate more computing elements into our introductory physics labs. And that is besides using Microsoft Excel for mostly data analysis. And with Python, and especially MicroPython, the version of Python that runs on our little circuit board, we can acquire data besides analyzing data. We'll still try to do our most data analysis in Excel, but this is something that you should be able to do. So let's go through the objectives. We just want to get familiarized with some physics constants as part of our calculations, and most of the objectives are on computing. So we have computing objectives under programming, MicroPython, and electronics. And in this lab, we don't need to do anything specific to MicroPython or electronics. So we're focused on just programming with regular Python or regular, just generic computer programming skills. So first we'll go through some math and logic, and then we'll use variables, and then we'll do some printing out of results, and we'll also do some importing of modules. So I'll skip through the introduction part of computing and Python, and just go directly to Thonny. Thonny is a Python integrated development environment, or IDE. This is on the right side. You're supposed to install Thonny, and we'll go through what the features that we use for Thonny. So let's see, we have this diagram here. You can also look at the right side. Here's a um, this is a directory tree. So this is the local files. I have the file. These are the files on my local computer. This will be files on the microcontroller board. Since we don't need the microcontroller boards for this, that is not displayed. And also I turn off the variable displays because I want the space to mainly be the program and this so-called REPL. This is the basically read, evaluate, print, and loop. So that's this. So once you have Python IDE, the Thonny installed, we can start using Python right away. So the download this and install, I'll skip it, and let's look at the rest of the steps. So the download link here, make sure you download the right version for your computer, PC or Mac or Linux. Um, so we'll start with basic math instructions. So now that it's running, so these are the things you need to understand between a Python and a pure mathematical expression. So a Python expression would require every operation, such as multiplication, to be explicit. And in a math expression, you can say, well, AB, that means A times B, but in Python, we must have the multiplication sign out. So here's an example, 3.14 times this. Well, that works in mathematics, but it doesn't work in Python because this will not be understood. What is 3.14 immediately followed by an open parenthesis? It will give you a syntax error unless you explicitly say 3.14 times it. So we can give this a try. Okay, so right here, basic is a syntax error. There's also some help coming out. That's fine. We'll skip it. So it's not understood. So what do we do? Well, we can press up button, recall this, and add the explicit multiplication. Then we get the answer out. So that's something you need to watch out for. Another thing is you have to close parentheses because this is absolutely necessary. It's also necessary in mathematical expressions, but you may have been spoiled by calculators that automatically close parentheses for you. Python simply just doesn't spoil people with that. You have to close any parentheses you open. Um, and then also the power function is slightly different. You may be used to this caret for power function, but in most programming languages, this caret means something else other than power. So in Python, power is a times, which is good because if you're using a keypad, like a numerical keypad, you don't have the caret there. So how do you raise power? Well, there's a times, just times, two times, and then you can raise the power, such as square 1.5, that is this. So 2 1/4. And then just another reminder of scientific notation, how it's written. It's written like this: 1.23 E4 is the same as 1.23 times 10 to the fourth power. So that's 12,300, I suppose. So that's similar, except that we don't really write it this way in mathematical expressions. But I think everybody understands this from their use of calculators. Okay. So now let's go ahead and do some calculations. These calculations are all physics related. So first we want to calculate the speed of light in vacuum, which is a 1 over the square root of these two numbers multiplied together. So they're products. So you don't need to worry about the units because they're all using standard units. And the result will be meters per second from the speed of light. So let's see. So how do I do this? Well, let's try. We'll try to enter these numbers, and we'll have a 1 over. So what I like to do is I like to lay out the structures first. So here is that 1 over square root, and then I want to multiply mu 0 with epsilon 0. So mu 0 is 4 pi over 10 to the second order. So now let's do this. 4 times pi is 3.1. 4, and then over 10 to the 7th power divided by 1e7. So 1 times 10 to the 7th power. So that is mu 0. And then we'll multiply epsilon 0, which is 8.85 times 10 to the minus 12. So e minus 12. So that would be the content inside of square root. And then you square root it, you do a 1 over. There we go. So what is this number? So is close to 3 times 10 to the 8th power. So that you can try shifting the digits and count, but that is a number there. So 3 times 10 to the 8th power, that's the speed of light in vacuum. Okay. So basically square root, that's just raised to the power of 1/2, right? And cube root would be, let's see, this is actually incorrect. There's a 0.5. Okay. Okay. So let's go ahead and do the next one. The next one is finding the orbital speed of Earth using kilometers per hour. So, well, orbital speed, that would be how fast you're orbiting. As Earth is orbiting the sun. We have the orbital radius. Okay, kilometers. Okay, sorry. For some reason, I probably copy pasted. All right, there we go. So the orbital radius is in kilometers. This is how far the Earth is to the sun. So that's the orbital radius. And then the period is basically 365 days and 6 hours. Okay, so then we need to find the circumference, which is the distance traveled. So you go in a circle, you find the circumference based on 2 pi times the radius, and that's the total distance you travel within the whole period of 365 days and 6 hours. Okay, so you can calculate this in steps, and eventually you have to do this in one step. So let's try this. We know first we need to find out the total distance, which is the circumference. So we'll do 1.5 times 10 to the 8th power times 2 pi. Okay, so that would be the circumference. Okay, so that divided by the number of hours, that will be in kilometers per hour, right? So how do we do that? And we can do 365 times 24 hours per day, and then plus an additional 6 hours. So this is how many hours. And all you have to do is to combine these two together. So that divided by that distance over time, right? So let's do that. 1.5 e 8th power times 2 times 3.14 and divided by 365 times 24 hours plus an additional 6 hours. Okay, so that would be, there we go. So in the order of, let's see, um, let's see, kilometers per hour. So that's 1, 2, 3. So 1,000, 10,000, 100,000 per hour. Let's see. Uh, okay. Okay, there we go. So next one, let's calculate the solve the quadratic equation. So we already have the quadratic formula. We just need to make sure we understand A is the quadratic coefficient, including the negative. So this negative 4.9 is A, and 5 is B, 2 and 2.1 is C. So we'll calculate this. We'll calculate both roots. And also we want to make sure we do explicit multiplication such as 1 over 2a times parentheses, right? So let's do this. 1 over 2 negative 4.9, so that's 1 over 2a, then times the whole thing is negative b, so negative 5. And let's do the plus first, then we'll do a minus, and then we'll do this square root, right? So that will be everything. So I'd like to see the structure, and then we'll fill it out with b squared minus 4ac. So b is 5 squared minus 4ac. That means 4 times a times c. So times negative 4.9, then times 2.1. Okay, so b squared minus 4ac, and the square root that, and then multiply this to the 1 over 2a. Okay, there we go. So that is one root, and we can recall this expression just by pressing the up button, and this is minus, so minus b plus minus, right? So two different roots. The other root is supposed to be a positive root. So this is actually a solution to a problem of if you toss a ball upward with a 5 meter per second speed and leaving your hand at 2.1 meters, that's just a little over your head height. And how long does it take to fall down to the ground? 1.3 seconds. Apparently, it's not negative time, right? Okay. All right. So doing this wasn't really the easiest. That's because we didn't use any variables, right? So if we use any variables, that will be easier because we can always store the values, such as we can say a equals this negative 4.9, b equals 5, c equals 2.1, and then all we have to do is to type up the expression, right? So let's go ahead and redo the above 3 examples, and we'll define some variables instead of typing up their values. So let's do the first one, redo the first one. We'll define a variable called mu0. There's just no Greek letter for that. I might be able to do that, but Python does understand Unicode, but let's not worry about it. I don't even know how to enter Greek letters. So mu0 is 4 pi over 10 to the 7th power, so 1e7. So defined. It doesn't print out, but if you want, you just type out the name, hit enter. Okay, there's the number. epsilon 0, you just say EP0 is equal to 885 times 10 to the minus 12. Okay, so there. You can also try to display it. And then the speed of light is much easier to express 1 over the square root. Just like again, I'll want to see the structure first before I fill it up. Mu 0 times epsilon 0. Okay, let's see what C is. Same number, basically 3 times 10 to the 8th power. Okay, so now let's look at the second question again. So the orbital speed as a variable of r and t. So we'll define r is the radius, which is 1.5 e 8th power kilometers. So there we go. And the t is, let's define this in terms of hours. So 365 days, 24 hours a day plus extra 6 hours. So that's that and that. So we can say v is equal to, did I say upper or lowercase? Lowercase. V is equal to 2 pi r, so that's the total distance, and over t. I see. Explicit multiplication, right? Easy to forget. So 2 times pi times r, right? 2 pi r is just too convenient for us. Okay, so there we go. Same exact number out again. And then solving a quadratic equation will also be easier if you define a equals minus 4.9, b equals 5, and c equals 2.1. Okay, so now with this, you can say root, these are actually time that we're solving, is 1 over 2a, but remember explicit multiplication minus b plus root, right? See the structure and then fill it. B squared minus 4ac, 4 times a times c. Okay, so this is a lot easier to type instead of trying to put the numbers in. So that's, how about we call that T1, so one of the roots. Okay, so then I'll press the up button and I'll recall this. And with the negative, I'll define it as T2. There we go. So what are the values? I can actually do T1, T2 with a comma, so both numbers will come out. It's a nice feature. Um, so now we have the same exact two roots again. So basically, this is just a practice, right? Just learn how to use Python. It's very similar to using a calculator. Even though you may not want to define variables in a calculator, it's a lot easier if you do define variables. You can sometimes even define a lot of these constants, such as mu zero, epsilon zeros are universal constants. You can also define things like radius, E, so that's Earth's orbital radius around the sun, radius RM, Mars orbital radius, things like that. So you can easily recall them in any calculations that use them. So that's the usefulness of having variables. And also you don't have to type up the numbers anymore. Okay, so let's look at things about printouts. So, well, you're printing your results just like a calculator, right? You type up something, you hit enter, the answer gets printed. But sometimes we want to format our printout. For instance, for the quadratic equation solver, maybe we want to print a line of text that says the two solutions are x dot xxx and y dot yyyy. We don't want that many digits. It's meaningless, right? I talked about this. If these numbers actually came from experimentation, which they could have, we have projectile launchers to the launch close to 5 meters per second speed. And we can mount it at a certain height to have the ball launched at 2.1 meters. So these can all be done in experiments. The numbers could have come from experiments, which means those are way too many digits, right? So we want to display proper amount of digits, for instance. So we have this, but we can also first order business is at least display something besides just the numbers. So that would require us to use the print function. So we'll do print. If you do anything in print, for instance, you can do that in double quotes. It'll just print that out. Pointless, but at least you get to see you print out what you type in quotes. So these quotes that we're typing, we actually put an F for formatting. So this is called formatted string. So the formatting comes from things other than the text. These are not formatting. This one, the following is a formatting, T1. We already defined T1 here, right here, and we got a value for it. So in the actual print, this whole set of curly braces with T1 will get replaced by this number. Nice trick, right? And then we can do the same thing with another one of these. Let's even add a period here. Still updating the rate up. Okay, so what this line of print will do is it'll print all that text verbatim, and then that same exact thing, but these are replaced by the variable names the curly braces are enclosing. So very long. We don't really need that. We want something shorter, right? So we want something that's maybe 3 digits after decimal. That should be good enough, right? So how do we do that? Well, here are the formatting. So we do T1, that's for sure, but we also want to indicate the formatting with a colon and then dot 3F. That means the dot it indicates the decimal point. 3F means 3 digits after the decimal, and the F means a floating number. You almost have to read this thing backwards. It's like floating number, 3 digits after decimal. So that's what the formatting will give you, and it'll print something nicely like this instead of a very long text. So again, we recall the instruction here. Just do colon. That is, what is the format of the T1 that you want to print out? You want to print out this, right? 3 digits after decimal, floating point number. You want to do the same thing for T2. So colon dot 3F. Hit enter. That looks really nice, right? No unnecessary amount of digits, right? Okay, so that's formatting. There's a lot of different formatting you can do, but this you can try and change it, try to hack it. For instance, what happens if you do .1F? Okay, that's going to only print 1 digit after decimal, probably too inaccurate for these numbers, right? You can also do something else with the formatting. But this is a nice thing to know that you can format your output instead of have your calculator like formats. Okay, so let's go ahead and do some modules. So what modules are? They're functions, features that can be pulled into your Python or imported into your Python, and then you can start using those modules. So that includes math modules, for instance, sine, cosine, all the trig functions, exponential, natural log, even a constant defined as pi. Um, they all reside in this math module. Um, Before you import them, you can't run it. You can say sine 90 at it's not recognized, right? Because that's not in there yet. So if you type up from math, import the star means import everything from math. So now you can run sine 90, which does not give you a 1 because all these trig functions, just like all the other programming languages, trig functions require um, readings for angles. So 90 degrees, okay, that's half a pi. So sine um, pi is actually a constant that gets imported from math over 2. So that's a sine 90 degree, which is equal to 1. And we can also type the quarter pi, that will be 45 degrees. That will get you a 0.707. So divide by 4. there, Simon '07. I memorized the numbers. So let's see. You also have the let's anything else. Let me see what we need. Okay, so we'll calculate this. Uh, 3 sine 15 minus 4 sine 15 squared. The cube. The cube is done after the sine 15 degrees. So let's try to express that. It's 3, our explicit multiplication, right? So 15 degrees. Okay, we can't do that with 15 degrees, but we can certainly call this a radians function that will convert 15 degrees into radians. Okay, so let's see if this runs. Okay, it does run, right? So let's call this back. Minus 4, again, multiplication, and I need to do the cube, and then I can fill in the sine of what angle? Radians 15 degrees. Okay. Um, an interesting number. You realize this is the same number as sine 45 degrees. Pi over 4 is 45 degrees. So for some reason, if you combine 3 sine 15 degrees with 4 cube of sine 15 degrees, you get the answer of 3 times sine 15 degrees. Well, sine 3 times 15 degrees. Let me correct myself. This is called triple angle formula. It's not really physics, but at least you get to know, oh, there's a triple angle formula. Sine 3 times 15 degrees is this expression. Okay, so that's how you would compare the two. They're supposed to be the same. Okay, so let's now calculate a natural log. So we'll do A. So we define this A as 100. Again, explicit multiplication, but we don't really have ln. Again, in almost all the languages I've seen, natural log is log, not ln. Now, if you want 10 base log, there's probably 10 base log where you type in the base or any base number. So here we have, so 100, natural log 100 minus 100. Okay, so that's going to be defined as A. Now you can see what it is. Okay, 360. Okay, so then we want to calculate the e to the 8th power, and that will be the exp function. So 8th power, there we go. It's a very large number, 10 to the 156 power. Most calculators can't do that. Maybe they can go up to 10 to the 99th, maybe even 100th power. Python can calculate much larger numbers than what we just saw. So it's no surprising that Python, I guess, used in simulations, astronomical simulations, financial calculations, anything that can involve very large or very small numbers, Python can handle them. Okay, so that, so we don't have the ln, it's actually spelled just like log. Okay, so now we want to calculate, let's see, something else. A natural log of 100 factorial. Okay, so factorial will have to require a function called the factorial function. So we'll spell this out as natural log, log, in Python. So 100 factorial, we'll do that. Okay, so this should be it. And are we supposed to do what's compare 2 with 3? So are these related? Okay, let's see if they're even close. Interesting. The A coming from the 2 calculation, 100 times natural log 100 minus 100 is 360. 360. If you round to even, 360. And well, natural log of 100 factorial is 364. Very close to this. And it turns out that there's an approximation, it's called Stirling's formula. In order to calculate the natural log of a large factorial, and you just do this. So instead of calculating 100 factorial, then taking its natural log. 100 factorial is very big. So, ooh, okay. So many digits. I can't even read this. All right. So it's a very big number, and then natural log that very big number. Instead of doing this, all you have to do is take the 100, never do the factorial, just try with the natural log, multiply 100, and then minus 100. So based on Stirling's approximation, the two numbers will be pretty similar. As you can see, they differ by what? 4 out of 360, so that's about 1%, so 99% close. So that should be it. So make sure you follow these instructions so you get to explore how to use Python as your calculator. It's free and open source.